Foam cell formation is one of the earliest and most critical steps in the development of atherosclerosis. When macrophages engulf oxidized LDL, ox-LDL, the resulting buildup of unesterified cholesterol within lysosomes can overwhelm the cell's ability to process and remove these lipids. This transformation of macrophages into lipid-laden foam cells marks the beginning of plaque development, initiating chronic inflammation, tissue remodeling, and eventual plaque instability. However, emerging evidence shows that niacin plays a decisive role in halting this pathological shift, reversing or even preventing foam cell formation by restoring lysosomal cholesterol export and protecting macrophage function. Niacin's protective action begins with its activation of CD38, an enzyme that catalyzes the production of NADP, a potent calcium-mobilizing molecule. This NADP signal releases calcium from lysosomes through TRPML1 channels, initiating a transcriptional cascade that activates liver X receptor alpha, LXRA. LXRA, in turn, induces the expression of key cholesterol transporters including NPC1, ABCA1, and ABCG1. These proteins work together to shuttle cholesterol out of the lysosome, into the cytosol, and eventually out of the cell, facilitating its transfer to HDL particles for reverse cholesterol transport. This process directly counters the core mechanism of foam cell formation. Instead of allowing cholesterol to accumulate and crystallize within lysosomes, leading to lysosomal rupture, inflammation, and cell death, niacin ensures that the cholesterol is efficiently exported before it becomes toxic. This reduces cellular stress and keeps macrophages in a functional, non-foam phenotype. In experimental models, niacin treatment sharply reduces the number of foam cells within developing plaques, even in the absence of changes to systemic cholesterol levels. Preventing foam cell formation is not just about slowing plaque growth, it's about stopping the earliest phase of atherosclerosis at its source. Once macrophages become foam cells, they not only lose their capacity to clear debris and resolve inflammation but also actively contribute to the inflammatory environment that drives further LDL uptake, smooth muscle cell migration, and matrix degradation. Niacin's ability to block this transformation preserves the regulatory role of macrophages in tissue homeostasis and immune modulation. Moreover, niacin's anti-foam effect is highly selective. Unlike synthetic LXR agonists that may cause unwanted lipogenesis in the liver, niacin appears to restrict LXR activation to macrophages under lipid stress, providing localized benefits without triggering systemic side effects such as hepatic steatosis. This makes niacin uniquely suited for early intervention, targeting the cells and pathways most at risk without introducing new metabolic complications. In essence, niacin performs a type of cellular sanitation, clearing cholesterol before it can hijack immune cell function and turn macrophages into foam cells. This not only reduces early plaque formation but also improves the quality and stability of the vascular environment as a whole. By preserving lysosomal health and enabling cholesterol efflux, niacin supports a more resilient, less inflammatory vascular immune system. In conclusion, niacin plays a pivotal role in reversing or preventing foam cell formation by enhancing lysosomal cholesterol export in macrophages. This action strikes at the heart of early atherogenesis, protecting vascular health at the cellular level and offering a proactive strategy for preventing the progression of cardiovascular disease. It reframes niacin not merely as a lipid-modifying nutrient, but as a first-line cellular defense against the transformation of immune cells into disease drivers.